Okay, so we are starting a new chapter, something that I think most of you are familiar with, nothing too fancy. We'll make it a little fancy, but not too bad. So we're starting chapter 7 that is dealing with radicals. And by radicals, we mean, oh, your square roots and cube roots. Those are the radicals. Every time you see that thing, it's called a radical sign. So first we introduce the square root. Or sometimes called principal square root. And basically the definition is the square root of A equals B means two things. One, B squared equals A, and two, B is greater than 0. And this part is somewhat important. We just want to make sure that every time we compute a square root, the answer comes out positive. Okay? I mean, there are two different square roots out there. There's just a square root. We don't even have a symbol for that. And they'll just tell you all the numbers such that if you square them, you get whatever it is you're trying to take square root of. So square root of 9 is 3 and negative 3. But that, we don't care about that one. We only want to have the square root that possess the positive result. So from now on, the square root of 9 is just 3, not plus or minus 3. The reason for that, do you remember our conversation about functions? No? Kind of? So if I tell you that, so let's say we have a function, don't write this down, that the function is square root of x, okay? So here's a function. And if I tell you that f of 4 is square root of 4, and then square root of 4 equals 2 and negative 2 at the same time, which means this function has these ordered pairs, 4, 2, 4, and negative 2. So my question to you, if you recall our conversation about functions a long time ago, can the same x correspond to two different y's? No, you won't know. Right. That's not good. We cannot have the same x value corresponding to two different y values and still be called a function. So this is why in order for us to work with the square roots in terms of a function notation, we only consider the positive result. So square root of 4 is 2, not negative 2. So we don't have that other ordered pair. Okay? So that's really straightforward. There's not much to it. So if I ask you some examples, if I ask you to tell me what is the square root of 25 is, you will say 5. And if I ask you what is the square root of 7 is, you will say, what do you mean nothing? What's the square root of 7? Well, nothing does not exist, undefined. Why? Why are you having difficulties with answering that question? So what you're trying to say, 25 was a perfect square, so no problem. 7 is not a perfect square, but it still exists, right? It's something probably between 2 and 3, right? So when we're left with numbers like this, square root of 7, well, that's just a square root of 7. There's not much you can do to that. But it's still a real number. It exists. And somewhere between 2 and 3, it's irrational, all that. But we can do that. All right, how about square root of 0? Why? When you're trying to answer the square root of 0, what are you looking for? What number are you looking for? 0, because 0 squared equals 0. So I should probably make a little correction here. B is greater than or equal to 0. So 0 is allowed. If I ask you a square root of 9/16, what do you think that is? 3/4. So we'll take the square root of the top, and we'll take the square root of the bottom. What if I ask you a square root of -9? Well, not a real number, right? So we do not know how to take square roots of negative numbers yet. Because again, by the definition, if you square something, it's just positive to begin with. So a is greater than or equal to 0 to begin with. Okay, well, what if I ask you a square root of 13 squared? What do you think that is? Yeah, that's just 13. All right, so square root of 13 squared is 13. How about square root of 13 to the power 6? What do you think that is? Why 4? Well, let's try. 13 to the 4th. So by the definition, if I square your answer, I should get whatever's under the square root. We call that the radicand. So this implies that 13 to the power 4 squared should equal to 13 to the power 6. Is that true? What do we do with exponents in this case? Multiply. So you get 13 to the power 8, which is not the same as 13 to the power 6. So now think about this. If you multiply exponents when you square things, what do you think you're going to do with exponents when you take square roots? Divide them. So what do you think then again? The square root of 13 to the power 6 is 13 cubed. Because if you square a cube, you get a 6. Is that okay? How about a square root of 1 and 9/16? Like that. But what's going to happen with the 1? Well, I mean, we have to understand what kind of a number is this. That's a mixed number. This really means 1 plus 9/16, right? So we did not have issues with this problem, right? When it was just a fraction, you went, oh, take the square roots of top and bottom, you get 3/4, and that's correct. Now this one is a little stranger, but that one was okay. So my question to you is, if you don't feel confident about this problem, and you felt confident about that problem, can you convert that mixed fraction to make it look just like just a normal fraction? How do we make our conversion between mixed numbers and just regular fractions? What is 1 and 9/16 equivalent to, fraction-wise? How do you convert from mixed number to improper fraction? Okay. Yeah. Or you just multiply 16 by whatever this number is and you add 9, that's your 25. That's how we convert. So when things are written in this form, can we take the square root of that when it's just 25/16? Yeah. So we get just 5/4. Right? If I convert this to mixed number, what would that be? What is 5/4 written as a mixed number? 1 and 1/4. So going back to the original question, can you just take square root of 9 and the 16 and left 1b, you'll get a different answer. Right? If you just take the square root of 9/16, you get 3/4, and you leave 1 as it was, you'll get 1 and 3/4, which is different. Okay, so the proper way to take the square root of a mixed number is to first convert to improper fraction, and then take the square root. That will be easier. Okay, now let me ask you a string of easy questions. Square root of 3 squared, we already kind of did that. Square root of 7 squared, kind of did that. Square root of pi squared. Can you tell me very quickly what are the values of these square roots? 3, 7, pi. Now, how'd you get those answers so fast? Okay, so that's one way to think about that. Is everybody happy with this? Squaring and the square root seems like two opposite operations. So you were just basically taking the base of that exponential expression. What if I ask you these questions? Square root of -3 squared, square root of -7 squared, and the square root of -pi squared. What do we get? +3, +7, +pi. Why? Okay, so if you follow the order of operations, you go -3 squared is +9, and the square root of 9 is 3, right? So following the order of operations, you get that. So it's not just simply dropping the power. We have to make sure we understand that, because if I just write -3, that's not the case, because I'm violating the definition. The square root can never produce a negative result. So in general rule, the square root of something squared equals the absolute value of that something. So you don't just cancel the square, you also have to make sure that the answer comes out positive. So when we'll be simplifying expressions that involve square roots, we have to keep track of that. Some exercises will tell you, assume that A is positive, so don't worry about the absolute value. If it does not say that, we have to make sure we include the absolute value. So this will guarantee that the answer is right, or comes out positive. Here's an example where it comes kind of useful. If I ask you what is the square root of 5 minus pi squared? So technically, according to that rule, this will be the absolute value of 5 minus pi. So this is the way you cancel the power and the square root. Well, now how do we take the absolute value of a number? We had a discussion about that a while back. How do we take an absolute value of a number? You just make it positive, right? If it's positive, don't mess with it. If it's negative, you make it positive. How do you make something positive when it's negative? What? No, you've gone in circles. You got back to the original question. We had that kind of a discussion again a while back. So if a number is positive, we don't mess with it. If a number is negative, you have to make it positive. How do you make a negative number positive? What? You put 1 on top of it? Well, I'm not sure what you mean, but no. What? Multiply by -1. That's how you change the sign. Negative numbers making positive. Multiply by -1. So when you're trying to take the absolute value of 5 minus pi, first you have to ask yourself, is 5 minus pi positive or negative? Is 5 minus pi positive or negative? Positive, because pi is 3 something, 5 is 5, so 5 minus 3 something is positive, so then the absolute value of that does not change, so just 5 minus pi, whatever that is. Right? Yeah. Yeah. So when you're taking an absolute value of a number that's already positive, you don't have to do anything. But if you take the absolute value of a number that is negative, for example, if I give you square root of, well, we can do 2 minus pi squared, something like that. So we'll start with the same process. The way you drop the square, you just take the absolute value, 2 minus pi. Well, since 2 is less than pi, 2 minus pi is negative, right? So we need to change the sign. The way we agreed, the way you change the sign, you multiply by a -1. Yeah. So it changes both signs. It's -2 plus pi or pi minus 2. It just kind of flips around the negative. Remember when we flipped around the negative, there's an extra negative, so that's kind of the same idea. Because 2 minus pi is less than 0, so this is why we have to multiply it by a negative to make it positive. How's that? Either this one or that one. Okay? I mean, mostly this is a better looking answer. Okay. So this is just a little exercise. So keep that one in mind. It's really easy to forget this little property. Okay. All right, so now consider the function So first of all, when we talk about functions, we talk about the domains. What do you think the domain of this function is? What can x be in order for this function to produce real answers? It has to be greater than 0 or 0. So greater than or equal to 0. Right, so the domain, you can say it's all non-negative numbers. Because if you plug in any positive number, you're going to get some positive number. If you plug in 0, you're going to get 0. But if you plug in negative numbers, you don't get real answers back. So that's the domain. So if I want to sketch the graph of this function, I can come up with a little table of values, my axis and f of x, and I can pick any x values, my independent x's. So I'm going to be very creative. I'll pick 0, 1, 4, and a 9. The numbers that are easy to take square root of. There's no reason for me to put in a 7 and then be stuck with a square root of 7. So if x is 0, square root of 0 is 0. If x is 1, square root of 1 is 1. If x is 4, square root of 4 is 2. And if x is 9, square root of x is 3. So I can plot these points. So here's 0, 0, 1, 1, 4, 2, and I don't know, 9, 3. So if I connect them, I get something like that. So it keeps going. It's kind of like half a parabola on the side. So this is the graph of y equals square root of x. So just by looking at this graph now, we can answer the range question. What is the range of this function? Just looking at the graph. Anyone? What is the range? Just by looking at the graph. What I'm asking for the range of the function, what am I asking for? Okay, so that's the domain. So domain is the x-axis. So if I'm asking for the range, I mean, we already stated the domain. What is the range? The y-axis. So if you look at the y-axis, what is covered on the y-axis by this graph? So it's the same, right? It starts, the lowest value is 0, then it keeps growing. This function will keep on growing all the way to infinity. So the range is the same as the domain. So again, just, I know we haven't done that in a while, but the domain is the x-axis, or the x values rather. But if you look at the graph, you just see what is covered on the x-axis, and the range would be the y values, the y-axis. So I can actually give you a function. For example, f of x equals the square root of 2x plus 1, and I can ask you find the domain of this function. So now we have to think about this. So before, when we were dealing with the domain questions, we only had to be worried about division, no dividing by 0. So that's what we did a while back, over a month ago. Now we have another issue. We shouldn't be taking square roots of negative numbers. When we look back at the original function, the x has to be greater than or equal to 0. Or in other words, whatever's under the square root, the radicand we call it, the radicand has to be greater than or equal to 0. So the way we find the domain of these types of functions, you're going to take the radicand. The radicand is 2x plus 1. And you want to make sure that that radicand does not turn into a negative. So you set it to greater than or equal to 0. So if the radicand stays non-negative, the function will operate well. So that gives you a very simple linear inequality. How do we solve that? How do we solve linear inequalities? Yeah, just solve for x. So subtract 1, and then divide by 2. So x is greater than or equal to negative 1/2. This would be the domain of that function. So the domain is, you can either write it as all x's such that x is greater than or equal to negative 1/2, or you can use the interval notation. But again, the general rule would be no matter what this is, you will take the radicand and you'll set it to greater than or equal to 0, and you'll try to solve that. So this will guarantee that expressions under the square root do not turn negative. Okay? So that adds another issue to our domain questions. Domain before was just make sure the denominators are not 0. Well, no denominators here, but now an extra thing is the square roots. You'll be watching out for the square roots as well. Well, try this one on your own. Find the domain of that function. So did anyone find the domain? Okay, let's try. So what did you do? What was the first thing? Well, before. What is your... All right, so 3 minus 5x. Okay. That's correct. So that's how we started these problems. Now what? All right, subtract 3 from both sides, so it's negative 5x is greater than or equal to negative 3 by 5, or... Okay, so divide by negative 5. Now, what do we need to remember? Yes. So when dividing by negative numbers, the inequality changes. So x is less than or equal to 3/5. So we have to watch out for that. So all those rules still hold. So, but yeah, the biggest thing you have to understand how to get those started. Now, so it's all x is less than or equal to 3/5, or from negative infinity to 3/5, including 3/5. What? Well, it just tells you the inequality. So it's everything less than, so you know it goes to the left. Or it's, in the first one was everything greater than, so it goes to the right. Okay, good. Now, of course, in addition to the square root, we have the nth root. So that's your nth root of a equals b implies that b to the power n equals a. And again, so that allows us to have two types of roots. We can have even and odd roots. If n, we call that the index of the radical. A is still the radicand. So we can have an n could be even, n could be odd. We can look at the 4th root. We can look at the 11th root. Now, again, even roots, make a note. Even roots only produce only positive results. Odd roots could be both. Could be both positive or negative. So a few examples. Again, if you understand the concept of the square root, the concept of the cube root would kind of be the same. The only difference with the cube root, you can take cube root of negative numbers and it will produce negative results. So with the odd roots, you can have negative in, negative out. But for example, if I ask you a cube root of 8, you will say, what? 2. And again, the reason for that, because 2 cubed equals 8. Right? I can ask you what is a 4th root of 16, and you will say 2, right? So it's 2 as well, because 2 to the power 4 equals 16. I can ask you what is the 17th root of 1, and you will say 1, because 1 to the power 17 equals 1. So any root of 1 equals 1, right? If I ask you in general, what is the nth root of 1, you'll say, well, it's still 1, because 1 to any power is 1. What if I ask you cube root of negative 8? Why positive 2? Because you're looking for a number such that if you cube that number, you get negative 8. What cubed equals negative 8, if possible? Negative 2, because the odd powers preserve the sign. So odd radicals can produce negative results. So that's okay, because negative 2 cubed equals negative 8. So that's all right. But if I ask you the 4th root of negative 16, you will say, well, that's a problem because 4 is an even number. So if I take any number to an even power, it will always come out positive. So I cannot get negative 16, so not a real number. Now let me ask you this question. Cube root of 17 cubed, 11th root of 12 to the power 11, and then, I don't know, 5th root of 7 to the power 5. Can we do those fast? What's the cube root of 17 cubed? 17. What is the 11th root of 12 to the power 11? 12. What is the 5th root of 7 to the 5th? 7, right? So kind of the same idea. If your index of the radical matches the power, they should kind of cancel each other. We have to be a little more careful, just like before, if I introduce negatives. But keep in mind that negative roots can produce negative results. So what do you think the cube root of negative 17 cubed is going to be? Negative 17. That's okay to have a negative results here. And then negative 12, and then negative 7. So with the odd powers, the negative sign prevails. If I put even powers, if I do the same set of problems, but let's say 4th root of negative 17 to the power 4, and, I don't know, 10th root of negative 12 to the power 10, and 6th root of negative 7 to the power 6, what are we going to get in these cases? If I introduce even powers there? But again, the order of operation. If you think about the order of operation, I have to take negative 17, raise it to the power 4. I'll get some ungodly number, but positive ungodly number. Do you agree with that? If I take a negative number to the power 4, I'll get a positive number. Well, then I'm going to take the 4th root of that ungodly number. It will be positive 17. So this is kind of the same absolute value situation. the powers don't just go away, it will also make sure that it comes out positive. So its absolute value of negative 12 equals 12. Absolute value of negative 7 equals 7. Even radicals can only produce positive answers. So as a general rule, if n is odd, then the nth root of a to the n equals a. So those powers just cancel each other, and you're left with the base. If n is odd, so if a is positive, you're going to get the positive answer. If a is negative, you're going to get a negative answer, which is okay. But if n is even, the nth root of a to the power n will be the absolute value of a. So always comes out positive. So if a is positive, the final answer is positive. If a is negative, the final answer is still positive because of the even powers. Even powers will get rid of that. We'll get rid of that negative. So a few examples. What if I give you a fifth root of 32 over 243? And I also tell you that 3 to the power of 5 is 243 to save you some headache. So 3 to the power of 5 is 243. So what is the fifth root of 32 over 243? Again, 3 to the power of 5 equals 243. So what is the fifth root of 32 over 243? 2/3, right? 2 to the fifth is 32, 3 to the fifth is 243. Well, let me ask you this question. Fifth root of negative 32 over 243. What will that be? Negative 2/3. Right? What about negative fifth root of negative 32 over 243? Positive 2/3, because that negative has very little to do with what goes on in the radical. So really it comes out to be negative of negative 2/3, which is 2/3. What if I have fifth root of 32 over 243 to the power of 5? Like that. What would that be? 32 over 243. What if I have a fifth root of negative 32 over 243 to the power of 5, like that? Yeah, negative 32 over 243. So again, odd powers allow to have negative results. What if I have a fifth root, well, let's go back to 2/3 to the power 10? What do you think that is? What? Why to the fifth? 2/3 to the second, because if I go back to that early example that we talked about, somewhere here, where is it? Or maybe not that early. Okay, I don't remember what that example was, but we were playing with something squared. You guys remember that? Yeah, that one. We'll realize if you take the square root of to the power 6, you're going to end up with the power 3. So in other words, the way we got 3, we were dividing 6 by 2. That's how we got 3. So because we realize when you raise power to the power, you multiply. So logically, when you take the root, you will divide powers. Wrong page. So yes, really what is happening is that you are dividing the power of the expression by the index of the radical to get 2/3 squared, which is 4/9. Is that okay? We deduce that property. So in other words, we have a definition of rational exponents. Because again, when we were playing with these examples, we realized in order to get the correct power, we had to take power from the inside and divide it by the power from the outside. That's how we got power 2. So in general, the definition of a fractional exponent, a to the power m over n, is the nth root of a to the power m. So the denominator is the index of the radical, and the numerator is the exponent, regular exponent. We can actually deduce this little rule that a to the power 1/2 is the same as the square root of a. 2 is the index of the radical. We don't write 2 on the square root. 1 is the power. So 4 to the power 1/2 is really a 2. Because the question is equivalent to saying what is the square root of 4. I can ask you to compute 8 to the power 2/3. Now, we just have to realize that the numerator is the exponent, the denominator is the radical. Okay? So if I do that, this is the radical, and this is the exponent, I can think of this problem as a cube root of 8 squared. And it doesn't matter whether I square on the inside, because of the commutative property of numbers. I can either do it like that, or I can do it like that. That 2 is about to disappear. These 2 are equivalent. So the other way, the second way, is easier. So I want to really think about this problem as the radical, then exponent. Okay, that's not a, there should be a 2 here. Right, so the exponent and the radical. So that is 2 squared, so that's a 4. So 8 to the power 2/3 equals 4. Take this cube root first, you get 2, then you square it, you get 4. Is that okay? Tell me what is 32 to the power 3/5 equals to? Six? How'd you get 6? Okay. Well, it's not 2 times 3, 2 to the power 3. Yeah, you are having a many problems. So yeah, but that's 8, right? 2 cubed. But yes, do the radical first. It's easier that way. Let me show you. Because really, again, it's either way will give you the right answer. 5th root of 32 cubed is the same thing. It's just a lot harder to compute. Let me show you on the calculator. Oh boy. If I go 32 and I take the 5th root of that, I get 2, and then I cube it, I get 8, right? But if I go the other way around, if I go 32 cubed first, I get unholy large number. And then I'll take the 5th root of that, I'll still get 8. So it's easier to take the radical first and then do the power because you're dealing with smaller numbers, right? Yeah? So this way we have all rules of exponents that are out there. So let's review. So now we have all rules of exponents. So we have a total of 10 rules of exponents now. So you know the friendly ones, a to the power n times a to the power m, we add exponents, right? We have that one. We have a to the power n divided by a to the power m, we subtract exponents. So these are the good and friendly ones. We have a to the power n raised to the power m, we multiply exponents. Then we have these rules. If you take a product to the power n, ab to the power n is the same as a to the power n times b to the power n. So the exponent kind of distributes through products. Doesn't work with sums or differences. We have special formulas for that. Same works for the quotients. A over b to the power n is the same as a to the n over b to the n. So you take the numerator and denominator to the same power. 6. A to the power 0, what is that? 1, provided that a is not 0 itself. 0 to the power 0 is undefined, unless you're using a Windows calculator. Did I show you that? Yeah? 0 to the power 0 is undefined. 7, negative exponents. Negative exponents are reciprocals. A to the power negative n is 1 over a to the n. In more general terms, if you have a fraction to the power negative n, it flips the fraction. It's b over a to the power n. The 9th rule, and this is what we just learned, a to the power 1 over n is the nth root of a. And 10, a to the power m over n is the nth root of a to the power m, or nth root of a, everything to the power m. These are equivalent. Okay. These are our 10 rules of exponents. Okay, good.